GBrochard, an energetic fellow who will tell us about energetic ions.
Yes, thank you very much. Okay. Thank you. So today I'll be talking about the impact of non-Maxwellian ions on plasma stability and confinement in tokamaks. So yeah, I would like to measure my co-author here, Japan, US, and Italy. So obviously do not hesitate to interrupt me for a question during the talk, especially for those of you that are not familiar with tokamak plasmas. Yeah, not like that. All right. So so in the first one, I will just discuss what are energetic particles and why they're important in burning plasma. Then I will discuss a method I've been developing at ITER to realistically model fast ion distribution in a specific space for stability and transport analysis, and then its application in actual experiments in the city of tokamak in California. So first off, so what are energetic particles? So we will only focus on the ions here, the electrons, fast electrons that are out of the picture here. So in tokamak plasma, so we need to reach high temperature of about 20 kiloelectron volts to initiate fusion reaction. So for that, we need to initially heat up the plasma, and then we need to maintain the plasma at burning plasma temperature. So for that, we mostly use energetic particles that have energies of about 1 MeV, which is much higher compared to the thermal plasma that is about 20 kiloelectron volts. And so, so like they compensate for the losses that are mostly due to both collisional and transport in tokamak plasma. And so there are two main sources of fast ions in experiments. So first, obviously, you have the fusion reaction that creates an alpha particle. And then you have all of the non-inductive heating techniques, such as NBI, which is basically you inject a neutral, 1 MeV neutral in the plasma, and high-severage ions. So you throw a wave in the plasma that excites the ion cyclotron frequency. So the fast ion mostly collide with electron, and because of that, they are fully out of the thermodynamical equilibrium. You can expect the thermal plasma to be more or less described by a thermodynamical equilibrium. So it means like thermal plasma can describe as Maxwellian, but it's not the case for the fast ion. So it requires a 6D kinetic description that usually you can reduce to 4D with energy parallel, so velocity along the magnetic field line and to the space. So under axisymmetry assumption, basically in the torus you have axisymmetry in the tokamak, and under zero averaging over the Larmor orbit.
Can I ask a very
important
question? So this fast non-Maxwellian electron,
ion.
Do we know their energy spectra? Is it like a power law?
I'm getting just actually to that. Right. To your question. So those distribution non-Maxwellian, they differ vastly from Maxwellian in both velocity and position space. So I will start here with velocity. So we don't see it very here, but this is energy in X and this is V parallel V in Y. So for Maxwellian, you have something like this, obviously, because it goes like exponential minus E. Okay, so it decreases like that. But in the experiment, it's much different. This is possible for an NDI case, so you have injection at even a pitch value, so V parallel V, of fast ions, and then they slow down towards the bulk plasma due to collisions. So like you have a slowdown the energy, and you have a widening here in the pitch space because of pitch angle scattering. So that's one thing. And in position space, they also differ vastly. You would expect distribution into this space. This is actually a polar plane in the tokamak. You would expect actually the density to be following the field line, because you have here the white line. But actually they don't, because fast ions are even more subject to drift in tokamaks than the thermal ion. For example, this is an alpha particle in the jet tokamak. You can see that it has it departs very much so from the field line because it drifts both in the vertical direction due to both the curvature drift and the gradient drift, because you have a gradient in the direction. So one can obtain numerically such distribution by solving the Popovic equation, and we'll be coming back to that later. So then the question is, now that we know what they are, why do we care about them? So we care about them because they are known to destabilize kinetic imaging stabilities that will modify the performances of burning plasma, which is very annoying for for plasma, as you can imagine. So one of the main impacts is a negative one, actually, is the transport of fast particle. So the fast particle, they will create a mode by resonating identically with the wave. For example, here you can see wave here in the polynomial plane. And so through this resonance, most of the ions, they give away energy to the mode. By doing so, they get transported from the core towards the edge. So here you have the density profile of 1V as a function of the radius. And so this redistribution of fast ions from core close to the edge actually means that those ions will not be available to thermalize and to give out their energy through collisions to the core plasma, which basically means that you will reduce fusion performances because you reduce temperature at the core of the plasma. So that's the general picture for impact of fast ion on stability and confinement. But actually, there's possibly another route and another impact on this that have been conjectured for actually a while, since the 90s, I think, that possibly fast ion modes could be driving zonal flows. They could be driving shear colloidal torque that are known to quench turbulence. And so this very simple relation has been put in place where you can have the evolution of the flow that goes like the damping of the flow to the collision and a drive term that is actually linked to the radial currents of fast ions that are transported from core to the edge. So you can see it as so because you transport fast ion, you create an electric field because of the charge separation, and then this creates a colloidal flow. So this has been conjectured for a while, but actually we have demonstrated this in gyrokinetic simulation recently, where actually you can compute this radial current by looking here at the velocity integral of the electromagnetic perturbation here, delta phi, exostatic perturbation delta phi, times the perturbation of the distribution of fast ion. And so when you look at the time history of the zonal flow in red in the gyrokinetic simulation, and you look here at d theta, you compute from this equation, taking the current into account, you can see that you have the same drive, meaning that actually, indeed, fast ion-driven modes, they can create zonal flow, which means in the end, we can have a much more complex impact on performances, because in some regime, you can actually have an increase of confinement because of the flow created by the fast ion. And actually, that's what we see experimentally in many plasma, at least in the distributed tokamak, where we have seen fast ion-driven modes responsible for the formation of an ITB. So ITB meaning that we have an increase of the barrier transport here of the core temperature in the plasma after the destabilization of the fast ion mode. So you can see in the simulation that those modes create this flow here that is very much shear that will quench the turbulence that occurs in the core of the plasma. So we see all of this when the saturation amplitude of those modes is rather low, which means that actually in that regime, like the transport due to fast ion will be marginal, which means that it will not impact very much on the loss of temperature, the loss of thermalization. And actually, this loss will be much more compensated by actually the quenching of the turbulence that occurs at the core plasma. However, there are more complex regimes where it doesn't happen like this. And actually, we saw this when we tried to measure actually those flow experimentally in more recent study experiments. So we have done with this color, you can't see anything. Okay, maybe you can look at the other screen. So you have the mode of the pattern here that actually changes the flow, but only transiently in this regime. And it does so because it's actually the mode is very strongly driven. So you don't have the formation of a barrier, and then you don't have a good impact on turbulence. So it shows in the end that the drive of the fast ion instability is at least one of the key components into the potential beneficial cross-plane interaction that can occur between turbulence and fast ion-driven modes. And so now we come to what are the drives for those fast ion instability. So as many instabilities, so like they are created through the free energy that exists in the gradients of the configuration. And again, in that case, it is the phase-space gradient of the fast ion distribution, actually in the local vicinity of where you have resonances between waves and particles. So as I said before, this space is actually 5D, so it's quite complex. but you can reduce something to a much more compact space using some specific property of tokamak plasma. Because in tokamak plasma, you have three different crossover portion that enable actually to treat the whole problem through an angle action amidement formulation, meaning that you can split actually the trajectory of a fast ion in a tokamak into three specific motions that are separable in scale, time scale. So first you have the gyro motion here, along field line, then you have the bounce here in the equatorial plane, and then you have the precession of per particle here in the other direction. So to each of those motions, you have an invariant that is linked to an angle and to a frequency that with which the mode will resonate. So the first, actually here, we don't care about this one, the magnetic moment, because this frequency is much larger than the frequency we see from instability in tokamak plasma. But like the next two are much more important. So you have invariance of energy because on small time scale, so because instabilities occur on time scale that are much smaller than the gradient time. And so you have this bounce time here that can interact with instability. And then you have a third invariant, which is the toroidal kinetical momentum, just simply because the Lagrangian doesn't depend on phi because you have axis symmetry in your torus. So in the end, the patterns can resonate with weight through combinations of this precessional drift here and bounce drift. So the general dispersion relation for these fast ion driven instability have been derived actually for a while in the 80s, originated by Liu Chen, where you can actually cut the problem in two. You can see that actually you have this dispersion relation with complex omega, where you have one term that is purely due to the MHD part of your problem, to the bulk plasma. And then you have a kinetic contribution that is actually the term the fast ion. And so this term, so it has a drive term here that depends on the gradient of the distribution in this constant motion space, common space, that amplify energy. And at the bottom, you have the resonances here with the different orbits that I mentioned before. So basically, what it means is like the sign of this term here will determine the stability of the fast ion driven mode. So in case it's positive, then you are driving this instability. You have what we call an inverse Landau damping. And then when it's negative, you have actually typical Landau damping. And so in this complex 3D common space, so you will drive the mode only in the vicinity of resonances. So actually when you meet this resonance condition here, I will not explain exactly, it doesn't matter. And so in this complex space, you can see all of those black lines that are the different available resonances for your problem. And the color map here is the driving term. So basically you expect to have a mode where you have a resonance and where the gradient here is large and positive. So all of this obviously shows you that the shape that you have for the fast ion distribution matters a lot in driving or damping those instabilities. And we know there's been some work that show actually that using a Maxwellian approximation for fast ion fail in most cases actually to assess the stability of fast ion driven modes in experimental configuration. And obviously, this is all of the complex nonlinear dynamics. Yes.
Why are we talking about that?
I'm sorry?
Are we talking about strap particles?
Both.
Why is it the Bannon orbits that matter?
It's a simple example to explain the three different motions in tokamaks. Here we are discussing both trap and passing particles. Okay.
I mean, are most of them trapped or most of them are passing?
The fast ion, you mean? But most of them are passing. Because, yeah. Depends. Yeah. Okay. So like the shape of the distribution matters a lot. And actually, in most tools that we have now to look at transport and fast ion instability, most of the code actually they use a Maxwellian approximation for fast ion, which is bad. And then we need to generalize them in order to use realistic distribution. So on the left here, you have something from the experiment. And on the right, you have its counterpart Maxwellian. And you can see that you have a massive difference. And so you will write the mode very differently. And so the hope is to be able to describe such distribution in that space for then be able to tailor the distribution in such a way as you are able to promote or to avoid specific instabilities that you want in order to enhance the core confinement of your plasma. And such a tailoring obviously requires you to perform cross-scale simulation in gyrokinetic code, and then to validate them on two experimental discharges. So we need to be able to couple those codes with such kind of inputs. So as I was saying, yes, so the gyrokinetic code, they can provide a realistic estimation of the confinement. And so we can initialize them with focal-plane code that are used to compute those distributions from the experiment. But those simulations are numerically expensive, which steady state, and usually they will produce something that is very noisy for this space. Those codes, they require gradient of this. So you can imagine that like any simulation that takes that as input will explode and we will need to nothing, which is why it's advantageous to use this COM space because it will reduce dimensionality and so have a much lower noise, obviously. And also because by design steady state, because in that space, the profile cannot relax. And finally, in that space, you can identify exactly the driving sources and everything. They help us to tailor distribution for control purposes. Okay, so now let's discuss the method, the method I've been working on at ITER to develop this analysis. So yeah, so at first sight you could say, okay, so it's just thinking to us about the change of variables. So like, why would you need a specific numerical method? Because you could say, okay, I have a bunch of markers that describe my distribution. Okay, so I just basically beam them into the space. They have a given weight. I have a given interpolation function. I know the volume of the cell. Okay, it's done. Issue is by doing that, you forget the Jacobian of the transformation. And this Jacobian is highly complex. It's numerical. So actually, you can show it goes as the inverse of the bounds or transit time of fast ion. As you can see, it has a very, very complex shape in this time space, which shows that like, the histogram you get here is very different, obviously, from the distribution that you actually have in the end. So the method we have been using actually to compute this is by initializing marker locally in this space, pushing them in time, and then computing from their orbit the bounds transit frequency in order to actually be able to do the transformation. And so for that, we have developed a code at ITER, which is IMAS compared to IMAS. Basically, at ITER is a standard that we'll be using to describe both experimental measurements, numerical simulation in a unique way as to all of the discharges that we plan to do in ITER will be done in the same language, in the same format. So this code will be able to interact with that. So, and also it's available in such a way that it can be used as a standard for the whole community of ASEAN guys in magnetic fusion. So we start from the limited equilibrium that we obtain from any source. From that, we create a grid, the COM grid in P phi, mu energy, so those constant of motion. Then for each of those points, we do an orbit tracing in CT to be able to obtain the orbits and to obtain the Jacobian and everything. Then we take kinetic input from a focal-plane code in the form of marker, any form, that will be into this regular space, energy, d parallel, RZ. And then using both the Jacobian and the distribution, we're able to obtain the actual distribution in COM space, along with the orbits in COM space, the toroidal, the bounce transit frequency, and the precessional transit frequency. And so all of that enables us to do all the transformation we want. So I will briefly talk about the topology of that space. So okay, so in 3D basically, so we use a Cartesian grid in COM space in order to avoid any kind of singularity that could be resolved. And for each of those colored points here, you see the different orbits that you can obtain from particles on the right in the plasma. So basically, using this grid, create a database of orbits that will allow us to do transformation from COM space to any coordinate system used by the gyrokinetic code at play, whether it's Boozer coordinates or any other set of coordinates. And through the orbits, we know also the toroidal and toroidal traces in time of the particle. And so through that, we can create numerically for any kind of numerical MHD equilibrium, the bound frequency, the Poisson frequency, and so you have all of the materials that you need to be able to derive the resonant plane for your wave particle analysis. So now we need to show that this workflow is working. And so for that, using this database suborbit, we are actually implementing a loop of transformation from the kinetic input from Foucault code. We go to common space. Then from the orbits, we go back to the original space, back and forth to make sure that we don't accumulate too much errors, showing that actually we can make transformation accurately. So we start from this distribution here, that is average over the space to look at just at density in the parallel plane. And so when we transfer it to common space and back, we obtain this. As you can see, like very similar. Actually, when you look at the difference normalized, you can see that we only have about 4% of error. It's mostly due to sliding, to vector techniques, so it's actually not relevant. So you have very good numerical precision for this workflow in the clinical space. So in university space, this is the same. So you have this kinetic input, and that after the first iteration, you obtain this. So you see that you have very, very few error again, so only 4%. So it shows that like you can use this actually to initialize your full F, your data simulation very consistent. Okay, so that now that we have the distribution, we need to be able to initialize them in gyrokinetic or MHD code. And so for that, we need to consider the two main types of code that exist. First, we have the delta F codes that only evolve the perturbed part of the distribution in the full F. So for the delta F code, you solve the Vassaf equation by having to know the equilibrium gradients, the gradient of F at fixed mu and parallel, and the gradient of parallel of F at fixed mu and position. And actually, you can get that from the common distribution. So from the common distribution, you create a spline, and from this spline, you are able to get the P5 derivative of the distribution, the triangle, the energy. And then in the end, through standard chain rule operation, you are able to obtain what you need in your gyrokinetic code, specifically directly from the common distribution. To test that, we have used a simple test. So we have initialized isotropic Maxwellian the code with a set of prescribed density and temperature profile. And we have done that because for that kind of distribution, we know exactly the spatial gradient analytically. This. And so the point is to compare this gradient to the numerical one we obtained from our numerical distribution. Oh, sorry. So what we do is like we compute this in a G-pitch RZ space. And so this is completed analytically. It doesn't matter. And this is what we obtain from the workflow. And actually, when you compare the analytical expression from the numerical one, so this is what you obtain from the common space thing. This is what you obtain from Maxwellian. So you can see they are very similar. You only have minor differences actually at the axis, which is actually physical, because actually it's actually the relaxation of the local Maxwellian that is not steady state, obviously. This is steady state. So this shows that actually we can actually now use this directly in delta F gyrokinetic code. Then for the full F code, you need actually to load the distribution along the entire orbit. So not in uniform space. So you need to load something like this. So these are obtained from open simulation. Actually, it's not steady state. Using our workflow, we can actually obtain something that is this function of the constant of motion. And so, for example, in the peak code, you would just basically like use the Monte Carlo same thing to actually initialize the distribution. In a grid-based code, just Gisela or like something like this, you are just basically looking at the values that are specifically at this grid. So there are other aspects we need to consider actually when we have strong anisotropy with high beta. First, we need to make sure that force balance is ensured for the metric equilibrium. So basically, we may need to start sometimes with anisotropic metric equilibrium when nabla P here cannot be a scalar. And we need to enforce quasi neutrality. Now, the density of pattern is 2D actually. And so then the thermal ion needs also to be 2D in order to enforce quasi neutrality as an initial condition in the gyrokinetic simulation. Okay, so now that we have discussed the method, let's see how we can apply it to an actual experimental configuration. And so we have chosen a shot in the distributed tokamak to conduct a benchmark through an activity that is undertaken by the ITER organization, so that I'm leading actually. So there are two sets of discharges here. So you can see here a spectrogram with a very different modes. So all of the white spots here are different kind of fast-and even modes. And so those discharges are very similar. The only difference is like in one case you have purely tangential beam injection in the bidirection. And in the other case, over a small time window, you switch the tangential injection towards perpendicular injection. And actually, when you see that in the experiment, you have this window here where you stabilize mode in that gap, which are called those modes that are called BA. And so basically, this is an excellent example to test our algorithm because we have here a clear change in fast-and even mode stability under a change of fast-and distribution because of the change in injection. So we will be in security modeling stability on 3 different time cycles before, during, and after the switch injection to look at mode stability. And this will serve as an internal basis of validation before we can then use our gyrokinetic tools to actually hopefully enhance performances in ITER by actually tailoring the fast-and distribution. And so far we have a lot of different codes that are done with benchmark, or not enumerate them. You can look at the slide later if you want. In the preliminary analysis, actually the guys at DSUD showed that the BAE becomes stable immediately at the substitution. So actually on a time that is much smaller than the typical sprint time of the fast lane, meaning that actually it's a change in the injection that causes the change in stability. And actually you can see that when you look at what they have from the experiment. So before the injection you have this, then after the injection you can see that you have a change here. Like so the peak is now closer to the lower value of pitch, which means that actually this small change in distribution changes stability. And then when you restore the distribution later on by going back to a parallel injection, then you restore the model as well. So our analysis in the gyrokinetic modeling is preliminary, but like using all of the framework I discussed, so we can already actually look at the resonances and see whether or not we will have a strong impact. So that's the resonance actually, the distribution adds the energy we were discussing before, this energy here. And so we have the gradient here. And so first, I wanted to actually show you that like adding a numerical distribution matters a lot here and compared to the Maxwellian. So you can compute the equivalent Maxwellian from this just by taking the moments and looking at the density, the temperature, and then from that you create a Maxwellian. So that's what you obtain. So this is a counterpart Maxwellian. And as you can see, so like it changed because like it's isotropic, but also like the amplitude is much lower actually at the relevant energy, which means that the drive of the fast and even node will be much slower. So basically, like the Maxwellian are much less likely to excite the BAE of those energies. And so for that specific case, we can look at the different resonance that it at this energy for this given mode frequency. So we have all of the black resonances. And so you will have a mode, you will have a resonance where the mode exists in some space. So basically, in red here, you have all of the particles that are fully contained within the mode in this kind of space. In green, it's orbits that are actually tangentially inside the mode, in and out, and the rest is they're out. So basically, you expect most of the interaction to occur in this zone. And so basically, it will occur, then the resonance will mostly occur at that point where the drive is strong, where you have resonance, and where you are inside the mode. So that's for the case before change of injection. Then when you when you switch the injection, actually drive goes up, and then you are away from the resonance. So basically, like this change of injection shows that you can actually damage the BAE. You can see also that the lines move a bit because the image equilibrium moves a bit. And then when you go back after the later times when the putback are injection, then you have again drive close to the resonance, which means that actually you can also drive the mode later on. So yeah, this is preliminary because the analysis is ongoing. And so actually we obtain results very recently from the Chemical GTC that we have recently interfaced with all of those numerical distribution in time space. So we have done preliminary electronic simulation with the code, looking at both parallel and perpendicular perturbation of the B field on the first time slice. And so we have obtained indeed a BAE that clearly that closely resembles to the one that actually was obtained in the experiment. We just need to make additional checks with the event continuum to see whether it's actually the mode that we wanted to see from the experiment. And so we have compared simulation from the realistic beam and from local and Maxwellian. So in this shows actually that the code is broken because the local and Maxwellian need similar results, meaning that like with the original code formulation and the new code formulation with the physical distribution, you have the same results. And then you have a much stronger drive with the of the electrostatic potential in time. So you have much stronger drive when you use the realistic beam for the simulation. And you can also see that it works when you look at common space. So with this realistic distribution, so you're looking here as a perturbation on the distribution in the linear simulation. So basically, like everything that pops out is a resonance. And so you can see here, you have two big blobs that emerge around this resonance in this resonance. And for the Maxwellian case, you see much more resonances actually that align in the simulation because actually they are isotropic, but you are much lower NBD. So basically, you're having less zoom. And yeah, so you see only two resonances here because actually the drive is only here, the relative distribution, and actually it's located everywhere with the Maxwellian. And yeah, and so now we doing linear simulation and nonlinear ones on all time slices to be able to do some validation with the experiment. So as a conclusion, we created a method to transform accurately distribution in time space. That's the relevant one to look at resonances interaction. It can be used as a standard now to initialize any code of the community that use fast science. We have tested the accuracy of transformations, the chain implementation, the method. So everything has been tested. And so now the perspective are to push this benchmark that I'm conducting with other people through the ITER project to actually validate our codes on the experiment and to then actually be able to use those validated models to do some pattern tailoring in order to actually develop high performance scenarios that we can actually mitigate turbulence. Okay, thank you for your attention.